Life is too short to work at a crappy company. That's why Software Engineering Daily is proud to be sponsored by Hired.com, the job marketplace for software engineers. If you accept a job through Hired, they will give you a $2,000 bonus. But as an extra bonus to our listeners, you can get an additional $2,000. That's $4,000 total if you sign up by going to softwareengineeringdaily.com and using the link on the right side of the page to sign up. Hired.com will set you up with 5 great companies for interviews. These are companies like Stripe, Facebook, Uber, companies you would actually want to work for, where you can go and learn the cutting edge of software engineering. Go to softwareengineeringdaily.com, click on the banner on the right, and try out Hired.com. Richard Golden is a professor of mathematical psychology and cognitive science at University of Texas at Dallas. He's also the host of Learning Machines 101, a podcast which provides listeners with a gentle introduction to artificial intelligence and machine learning. Richard, welcome to Software Engineering Daily.
Hi, I'm happy to be here.
Let's start out with a straightforward definition. What is machine learning?
Well, that's an interesting question. What is machine learning? I would say that machine learning is a particular branch of artificial intelligence, which focuses more upon statistical aspects of learning, where you're trying to pick up statistical regularities from the environment or model statistical regularities in the environment in order to make intelligent inferences.
What are the fundamental concepts to building a machine that is artificially intelligent?
Well, the first most important fundamental concept is getting the right feature representation. If you don't have the right representation, then the problem can be very hard. But if the feature representation is right, then the problem can be very easy. So that's kind of perhaps the most important ingredient. And then after that, then the next issue is sort of trying to understand, and this is related to the feature representation issue, is trying to understand the problem domain and trying to incorporate constraints from the problem domain into the design of not only your architecture, but maybe even the learning and inference algorithms as well. When people, for example, are trying to make inductive inferences, they use prior knowledge about the world, and if you can incorporate those sort of prior knowledge constraints into your system, then you're going to make better inferences. Of course, if those constraints are wrong, then you'll make worse inferences.
So I've heard machine learning as described as the art and science of teaching computers to identify patterns and learn rules. And certainly in some of your work, I've seen the emphasis on the idea of rules. How would you define a rule in the domain of machine learning?
A rule is basically an if-then statement, perhaps sort of like in a production system. You have rules for given certain conditions hold and generate certain actions. But I would say that this sort of more logic-based component is probably less of a central component of machine learning. And in my podcast, I talk quite a bit about logical rules, especially at the beginning of the podcast series. I do that because this is fundamental to sort of understand the role and limitations of rules, and so how we can kind of go beyond that. In the real world, it's very difficult to represent knowledge as a collection of rules, and I think that's where machine learning really sort of comes in, where machine learning really shines in dealing with the fact that the knowledge in the world is very difficult to represent as a collection of rules.
You've mentioned feature generation. How is the idea of feature generation related to the creation of rules?
How is feature generation related to the creation of rules? Well, when you have a rule, you're checking to see whether certain conditions hold, and then if those conditions hold, then you might generate certain actions. Well, how do you define those conditions? So, for example, consider a chessboard, and you're going to make a move. You could say, well, my feature is going to be a grayscale image representation of the chessboard. Well, now you've clearly, if you make your features to be little pixels with little gray levels, clearly you're going to have a much harder inference problem. On the other hand, if you make your features more abstract, such as the locations of the pieces on the chessboard, then things will be easier. And if you make it even more abstract features, such as my opponent is laying a trap for me, I've got to kind of escape from this trap, then that's even more useful. So that challenge, of course, is where do you get these abstract features? Okay, so traditionally, like in the 70s, these features would be hand-coded, and they're still hand-coded even today. But there's been a lot of work, for example, in trying to extract such more complex abstract features automatically from the statistical environment, perhaps using some of these deep learning methods. It's an open area of research. Some people will say that learning these abstract features is the way to go. Other people will say you're never going to be able to learn them. You're going to have to hand code them. Ultimately, I think the problem is got to be some sort of combination of these approaches.
So in the real world, there are always edge cases that smart machines have to deal with. Like if an autonomous car is sitting at a red light and the light turns green, generally the car should go unless there's a person walking in front of it. So this can be this can create complex examples that have sets of rules that could be contradictory or hard to disambiguate. How do you avoid making rules that are inconsistent? How do you create a system that allows a smart machine to make progress even when there are two conflicting rules?
Well, that's where the statistical component of my definition of machine learning comes in. Is if you take sort of a probabilistic view of reality rather than a deterministic view, then things look a little different. So I remember when I was a graduate student, I was sitting in the office of my advisor in electrical engineering, and he said, "Look at that window. You see a Volkswagen. I see a realization of a random variable." So the point is that if we instead say, well, there's this high probability that we should do something under certain conditions, and there's a high probability we should do something else under certain conditions, then we can use these probabilistic representations of reality to make inductive inferences, such as, well, what's the most probable action should I take given these circumstances? The challenge in this situation, of course, is how do you write down these probabilities in such a way that they are consistent? And there are definitely techniques that have been developed to do that.
Smart machines often get into situations that lack certainty, which can be related to the previous example of the autonomous car in front of a green light with a person in front of it also. In Learning Machines 101, you talk about using fuzzy set theory to help make inferences in uncertain environments. What is fuzzy set theory?
Well, the idea in logic, for example, if I say, if I am a dog, then I'm an animal. In logic, we could think of logical rules as corresponding to set theory representation. So the set of dogs is a subset of the set of animals. And so in fuzzy set theory, we allow partial membership in such sets. So we can have a particular object which can be only partially member of a set. And so the degree of membership, so associated with each set, is what's called a degree of membership function, which indicates your degree of membership. So you could develop a whole set of not only fuzzy set theory, but fuzzy fuzzy rules to make inferences about the world. In probability theory, we actually assign degrees of belief or probabilities to crisp sets, to sets which are more traditional, where you're either in the set or you're not in the set. But so in some sense, the probability theory entails a sort of logical, non-fuzzy view of reality. But in fact, when there have been theories developed which allow for even more extreme representations of uncertainty, where we can represent the world in terms of fuzzy sets and assign degrees of belief to these fuzzy sets.
How can a machine learning system estimate the probability of something that it has not seen?
Well, the basic idea is to represent the probability of something you have not seen is you have to make certain assumptions about what the probability distribution is that you are trying to learn. So, and these assumptions are often called smoothing assumptions. So the basic idea is that if there's a certain if you don't see something, but you know the probability of something that is very similar to that thing, then you might sort of estimate the probability of the unseen thing to be similar to the probability of the thing you have seen.
In machine learning, we often talk about models. Can you describe exactly what a machine learning model is?
Well, models mean different things to different people. But in the context of machine learning, and specifically statistical machine learning, a model refers to a probability model, to a collection of probability distributions. And the real world is presumably one of these probability distributions. The real world presumably generates data according to some probabilistic law. And the goal of the learning machine is the learning machine has a model of reality. It has a collection of possible probabilistic laws that might represent reality. And the goal of learning is to try to pick out which of those probabilistic laws is the best model of the probabilistic law which is generating the data.
You describe statistical gradient descent as the fundamental principle underlying learning in the majority of machine learning algorithms. How does statistical gradient descent work?
Well, the basic idea of statistical gradient descent is that in regular gradient descent is the basic idea is that we have some function which we want to minimize, and this function is a measure of the performance of the learning machine. And so the idea is the learning machine adjusts its parameters such that it can optimize its performance. Now, this performance function presumably is dependent upon the knowledge that the training examples that you provide the learning machine. But in the real world, we might not see all the training examples. We might not have all the training examples available for the learning machine. The learning machine might be interacting with the environment, and training examples come in one by one. So in order to, so the learning machine never actually ever sees the objective function that it's trying to minimize. So what it has to do is it has to use the training example that it's currently viewing, or the training examples that it's viewed so far, and estimate the objective function that it thinks it would see if it had kept observing training examples into the future. And the estimation approach in this case, in the example you mentioned, statistical gradient descent, is basically you twiddle the parameters in such a way that the value of your performance measure, which measures the performance of the learning machine, decreases just a little bit each time you see a training example. But it's important to understand that the function that you're minimizing is is actually a function that's not observable. It's a function of the training data that not only you've already seen, but also training data that you'll will see in the future, that you expect to see in the future.
You have one podcast episode, or at least one, about Monte Carlo Markov chains. Why are Monte Carlo Markov chains important to machine learning? Maybe you could describe what they are.
Sure, absolutely. So the concept of basically Monte Carlo Markov chains are good for two important tasks. One task is the problem of stochastic search. And the other task is the problem of computing complicated integrals or summations. So let me kind of focus on the stochastic search example first. So lots of times in artificial intelligence, we are faced with the problem of search. We have a bunch of possibilities and we want to try to pick the best choice. And if the search space is very, 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 very large, it may be impossible to search a significant percentage of that space using even the most advanced deterministic search algorithms. So then you would have to resort to a method of stochastic search where you randomly visit different points in the solution space. And what the Monte Carlo Markov chain algorithms have been around since the 50s, but the basic idea is that you create this crazy way of randomly wandering around the state space in such a way that the solutions that are the best, corresponding to the best performance solutions, are visited more frequently. And so because they're visited more frequently, what you basically do as you're sort of making this random wandering all over the state space, which might be extremely high dimensional. I mean, the dimensionality of state space might be, easily 2 to the 10,000 or something bigger than that. Okay, I'm talking big. Because with modern computers, a state space of 2 to the 25th, you can, if you soup up your machinery, you can do an exhaustive search of it. So you wouldn't want to use this type of technique on something like that. But when you have an enormous search space, then what you do is you sort of randomly wander around the state space, and the mathematics is such that you will tend to visit the higher probability states more frequently. Now, this is you have to be kind of careful with the use of these algorithms because you can sometimes fool yourself into thinking that you've got to a good solution when really you haven't. But the way people deal with this problem is they just run the algorithm, like, for example, a second time, and if you go to some place which is totally different, then you say, that's something we need to take into account. So as you're wandering around the state space, you just keep track of the best solution, and that's what you use when you're done. Now, I was just going to say is that there's another application of Monte Carlo Markov chain, which is evaluating summations or integrals or expectations. And many times in machine learning, I give a good example. Let me give you a little more concrete example. Suppose you had a prediction problem, and you were trying to predict a particular quantity of interest, and you had, say, 1,000 possible features that you thought would be good for predicting that quantity of interest. So you've got 1,000 possible predictors or features, and you don't know which ones to include in your model. So basically, the way you could think of this is you have 2 to the 1,000 possible models to consider, or 2 to the 1,000 minus 1 possible models to consider. Well, one approach if we do a stochastic search approach, we could kind of wander around the state space and using the Monte Carlo Markov chain method. And since we're visiting the models that are the best most frequently, then we can just kind of keep track of the best model. And I've already kind of gone over this, but this is perhaps not the best way. I mean, if we think of this from a simple example, suppose you wanted some sort of expert opinion on how to solve a particular problem in nuclear power plants. Then you might go all over the world and collect a whole room of experts who are all experts in nuclear power plants. And then once you got them all into the room, it might be thousands of experts are in the room. Then what you would do is you would say, okay, now which of these guys is the best expert? And you find the best expert and you say, okay, the rest of you can leave. Okay. So that wouldn't really be the best way to use all of those experts. A better way to use all of those experts would be to rate each expert according to their dimension of expertise. And then when you had a particular problem in nuclear power plants, you would compute sort of a weighted average of the opinions of all the experts in the room in order to answer your question about nuclear power plants. Now, this weighted average would be pretty big because you might have, thousands of experts in the room. Well, similarly, in what's called model averaging, one might make a prediction. Instead of trying to look for the best regression model, the best predictive model in this big model space, what one does is one computes a weighted average of the predictions of all the models you visit in your stochastic search, where you weight the prediction of each model that you visit randomly in this random walk. You weight it according to the expertise associated with that model. And since you're visiting models that are more effective predictors more frequently, this tends to give you a weighted average, which is going to give you especially good predictions.
Is there a particular vocabulary term for this idea of getting a weighted average of a bunch of different?
Yes, the technical term is called Bayesian model averaging, BMA, and a less well-known variation of this is called frequentist model averaging, FMA. And if you go to Wikipedia, you can probably find an entry on that.
Okay, interesting. So your website has some examples of machine learning applications that you've been interested in. Many of them are medical scenarios, like predicting the risk of multiple organ failures after severe injury. Could you explain how machine learning can be effectively applied to one of these real-world scenarios?
Well, the way we've been in that type of application, we're actually doing something similar to this model search idea. We search through the model space for. First, we get some features, and we select the features in the presence of a domain expert. And then once we've got these features, then we construct a model space and do a stochastic search of the model space. And then once that stochastic search is completed, then we do a deterministic search for the best model. So this is one. So the techniques that I was sort of referring to that's the kind that we've been exploring in practical applications.
Okay, interesting. So let's talk about neural networks. What is a neural network? How does that apply to machine learning?
Well, the term neural network it can mean different things to different people, and if you I think that if you went to a neuroscientist, they would say, well, a neural network is a particular circuitry in the brain, okay? But most people in the machine learning literature use the terminology neural network to refer to a network architecture where you have inputs which feed into one layer of pre-processing transformations, which feed into another layer of transformations, which generate a prediction. But there are many different types of there are many different sort of ways to interpret sort of the phrase neural network. I like to think of the phrase neural network more in the terminology of I only use the phrase actually when I'm actually trying to make a abstract model of the brain or talking about an abstract model of neural processing. Otherwise, I prefer to use the term machine learning. Typical terminology that people use for the term neural network is neural network is typically in the machine learning literature a way of learning features as well as using those features to make predictions. So the features themselves can have parameters in them, and you can learn the parameters of the features as well as learn how those features make predictions. And this is an old idea. This is not really such a new idea. For example, if we do a Fourier analysis where we represent a time signal as a weighted sum of sines and cosines, we could think of that, if you want, as a neural network where the basis functions, the cosines and the sines, correspond to the features of the time series. So the idea of pre-processing transformations and computing weighted sums of basis functions is a pretty well established idea in literature.
Over Thanksgiving, I had a great idea for a web app. So instead of spending time with my family, I locked myself in a room and I started building this application using Express.js because I love full-stack JavaScript. So I was testing my application locally and I was making great progress. So I decided to deploy it and share it with some of my friends and get some feedback. I used DigitalOcean. I signed up for an account using promo code SEDaily, and in 15 minutes, I had my app deployed to a server and running. It was that simple. This was really the first time I had used DigitalOcean. So if you're like me and you like building stuff and you have ideas for projects, give DigitalOcean a shot. It is the fastest and simplest way to deploy an application that I've ever used. If you want to give it a try, go to DigitalOcean.com and use the promo code SEDaily to get $10 in free credits. Check it out. Speaking more specifically about terminology, there are the notion of convolutional neural networks and recurrent neural networks. Could you distinguish between these two?
Sure. So the basic idea of a convolutional neural network is that what you're trying to do is and these have been, by the way, extremely successful. They've been used in a variety of ways and have been extremely successful. But the basic idea is that you have an image, for example, and if you learn a particular feature in one part of the image, then you would like to be able to generalize and detect that feature in another part of the image that was never presented before. So in a convolutional neural network, you have these features which are used to examine which process information from a particular region of the image, and then that same feature is then perhaps moved a little bit and it's used to process a different part of the image, and then moved again and used to process another part of the image. And as a result of this feature sort of moving across the image, it generates a feature map, which can then be used to generate a recoded representation of the original image in terms of these more abstract features. And then you can have another layer of features processing this feature map in a similar way. And some of the more successful deep learning machines have actually used these kind of convolutional maps to represent actions on Atari video games. And the lower level features pick up things like small little graphical features such as like horizontal line segment here, visual line segment there. The next layer of processing, picks up more abstract features such as this is a little object here and there's a little object there, and then maybe at near the highest level you might have representations of particular situations that need to be avoided or dealt with.
So I watched a talk by Jeff Dean of Google, and one of the interesting things that he said in that talk was an important property of neural networks is that results get better with more data and with bigger models and with more computation. And I thought it was an interesting property because it's not necessarily true about systems in general. Like I feel like if you grow a system in general, a lot of times it just becomes more bloated and harder to deal with. So I'm curious what you think. Like, do you agree that it's true that neural networks just basically get better with more data and bigger models and more computation?
No, I actually think that the statement made by Jeff Dean was kind of an oversimplification. I actually kind of liked your comment about the situation a lot better. It seems more appropriate. It is much harder to deal with. The systems do get more bloated and more difficult to deal with, and these deep learning systems are bloated and difficult to deal with. It's not the case that just as you collect more data that things will always get better.
Yeah, I don't know if you read this paper by D. Scully that was like it was called "Machine Learning: The High Interest Credit Card of Technical Debt." So it was like. He just talked about like machine learning has all these properties where it leads to a glut of technical debt. But again, that doesn't really contrast with what Jeff Dean was saying, I don't think. But there is something there. So yeah, in episode 23 of your show, you discuss how to build a deep learning machine. What differentiates a deep learning machine from a typical machine learning system? Or I guess a non-deep learning system.
I would define. So it sort of depends how you define deep learning. But if you define deep learning as typically, I guess I would make the distinction between learning problems which are what are called convex versus non-convex learning problems. So a convex kind of learning problem means that as the learning proceeds, you're guaranteed to get to a unique global solution, or maybe not unique, but a global solution. And the learning process is pretty straightforward. And the deep learning machines where you're actually learning the features, you're discovering the features that you need to solve the learning problem, I think that's sort of the critical distinction. So in traditional machine learning, you are given the features, and in deep learning, the main goal is to sort of discover the features. And those features are actually hierarchical. So it's not like you just discover features at one layer, you discover features at sort of the lowest layer, and then you discover features which represent interesting combinations of those features, and then you discover other features which are interesting combinations of those features, and onwards and upwards. So that's, to me, the fundamental characteristic of deep learning. People who are doing deep learning are really interested in taking a complex problem and not applying a divide and conquer strategy, but rather trying to sort of learn the entire problem at once, features and relationships among features, and then intermediate features and relationships among intermediate features, and higher order features and relationships among higher order features, and learning all of these simultaneously.
Why are convolutional neural nets so important to this feature discovery and this deep learning?
Well, I'd say the convolutional neural networks are important because they have worked really well. I mean, they've solved a lot of problems that people had difficulty solving before. So I would say that's, I think, sort of the fact that they work really well is where there's sort of a lot of interest in them. Sometimes people will say, referring to the deep learning or the convolutional neural networks, they'll say, well, this is based upon how the brain works. And you have to be really careful about statements such as this. This is kind of coming back to the neural network question, because the brain is extremely complicated, and saying this is the way the brain works is as the explanation is sort of like saying this is the way the world works. It's just kind of a broad. You have to say explicitly, well, what aspect of the brain am I modeling, and then is this successful at modeling this aspect of the brain? The example I give to my students, I think I've mentioned this in the podcast too, is the McCulloch-Pitts formal neuron. So the McCulloch-Pitts formal neuron was actually invented in the 1940s, and by a neuroscientist and a mathematician. The neuroscientist was McCulloch, and the mathematician was Pitts. And they were trying to build a mathematical model of how neurons work in the brain and how they generate interesting computations. And they modeled the behavior of a neuron as computing a weighted sum of its inputs and then seeing if that weighted sum was greater than the threshold. And if it was, then the neuron would emit a spike. And that was consistent with what they currently knew about neuroscience. And in some sense, it's consistent with what we know about neuroscience today. They showed that you could wire up any collection of these McCulloch-Pitts formal neurons and realize any logical function. And that was very influential in the design of the modern digital computer, and these McCulloch-Pitts formal neurons turn out to be logical AND gates and logical OR gates and NOT gates. And so you can realize any logical function. And this is a network. This logic network is inspired by the brain. It turns out that even though it was sort of an abstract model of the brain, it turns out that the features of it as sort of a model for neuroscience turned out to be flawed later on. They were due to the fact that information in the brain is really represented in terms of firing frequencies. So the output of a neuron is best represented in terms of its informational features, in terms of a firing frequency. Other researchers have shown that neurons have linear response properties in many different situations. So linear systems are an example of a neural network as well. But so you wouldn't justify. So you could say, well, I can also justify why am I using this linear system? Well, it's because it's inspired by the brain. Okay, so this explanation of that it's inspired by the brain, I think, is is a little lacking.
Well, to leverage that lacking analogy, you do talk about how you can improve deep learning performance with artificial brain damage. What do you mean by that? So basically, the artificial brain damage in this context is what's referred to as a phenomena or an approach which is called dropout, which is a form of basically the basic idea of dropout is we have a deep learning network where we present it. Input pattern comes in and it's processed by the first layer of units, and then the next layer of units processes that input pattern, and then the next layer of units processes the output of that layer, and so on. And in dropout, what you do is each time a pattern is presented, then the connections among the units are strengthened and weakened. So the basic idea of dropout is that after you present, or when you present a particular input pattern, you randomly ignore a subset of the nodes in the network, and you just update the network based upon the nodes that are not ignored. And this seems like sort of an odd kind of thing to do, but the basic idea is that by doing this, this prevents some of the nodes in the network, or prevents a lot of the nodes in the network from sort of
look, coming along for a free ride. If you're in the network and you're not doing any work, then you're going to get penalized. And it can actually be shown that this type of method for dropout is extremely effective. Pretty much many of the successful applications of the deep learning method use this dropout method, and it can be shown to actually be mathematically equivalent to a form of this model averaging technique I talked about earlier, where you're simultaneously learning to strengthen and weaken the connections of a whole bunch of networks and then averaging the results across them.
You are a college professor, and you spend some of your time teaching students machine learning. When you teach students, what are the biggest conceptual hurdles about machine learning that those students have trouble with?
Well, it depends upon what course it is and who the students are. But in the introductory course, I think one of the big conceptual hurdles is the idea that when you're learning in a machine learning environment, it's not like the knowledge is immediately accessible. So like in a normal database, you could say, okay, here's the knowledge. It's a bunch of these rules, okay? But in most machine learning applications, the knowledge is just a bunch of parameter values set to particular numbers. And so it's a little hard for students to figure out how knowledge is represented and how inferences are made when all you see is just sort of a bunch of numbers. Now, for the more advanced students, usually the challenges are in terms of seeing how the abstract mathematics that's really necessary to sort of understand these machine learning algorithms sort of comes to play and is relevant to particular practical applications. So,
and you're the host of Learning Machines 101, which is a pretty cool podcast about machine learning. I've listened to it a fair amount. Why did you start Learning Machines 101?
Very interesting question. So I will reveal the answer for the first time on the air. Basically, I have been working on a book for the last 6 years.
Oh.
And the book is titled, it's Foundations of Statistical Machine Learning. And I decided that it would be important to identify who my potential readers were before the book is published. And so I decided to launch this podcast. My first book was published in 1996, and it was called Mathematical Methods for Neural Network Analysis and Design. And it was fairly successful, but it wasn't as successful as I really wanted it to be. And since 1996, the book publishing industry has changed quite a bit. I mean, now that you don't really go into bookstores to buy books anymore. Usually go online and buy stuff off Amazon. So there's a lot more competition for people sort of seeing, finding out about sort of what your book is about. So I thought, well, a podcast idea might be a really great way for me to sort of collect and identify people that would be interested in this type of material, which is a little abstract, but sort of collect these people from all over the world, in addition to sort of collecting people by going to scientific conferences and, collecting people at that level too, but I sort of was trying to collecting people in the other direction as well. And so so that was my idea, is that I should, could give this podcast, and then the book is actually aimed at sort of not everybody that would actually listen to this podcast. The podcast is aimed at a more general audience, but I figured that if each person that was listening to my podcast knew one person that would be interested in my book, then that would definitely be a good situation for me, and for other people regarding my book. But what my book is about is it's about when you're coming up with sort of different machine learning algorithms, how to prove theorems and make design choices so that those algorithms will behave properly and make proper generalizations. So it's sort of a theoretical foundations for machine learning.
Do you have a release date for that book?
No, I do not. It's going to be pretty far into the future. We're talking about, I would say, it's going to be several years in the future. Even though I've been working on the book for 6 years. The book's kind of complicated, and I want to make this complicated material really accessible. And so there's sort of multiple challenges: is how do you make very, very complicated material very, very, very accessible?
Yeah. Do you feel like you're like racing against the field also? Because like the field's advancing pretty quickly also, but I don't know, maybe the fundamentals don't change rapidly enough to make it big.
Well, that's a great question. So in fact, the fundamentals don't really change. So it's not like the stuff that I'm talking about was relevant, a long time in decades ago, and it'll be relevant, I think hundreds of years into the future. Okay. The real question is the examples and the problems. The examples and problems can be outdated very rapidly. So you might have this really great way of doing a mathematical analysis of a machine learning algorithm, but if your examples are machine learning algorithms from the 1980s or 1990s, people aren't going to be very interested. But if you give examples of how your analysis works, of how to do analyses, and the examples you give are examples that from the 21st century, then people are going to be, hey, this is really cool. So another thing I've started to do is I started to I went to the machine learning conferences years ago, and now I'm beginning to go back to them to sort of find out what are the current architectures that people are most excited about, and trying to put those in as examples of applications of the mathematical analysis. So. So that's I don't know if that is helpful. But anyway, that's kind of what I'm doing. So
yeah.
But also the podcast has sort of taken on a new life of its own, as you might have expected. So it started off as sort of to support the book, and now it's kind of got its own kind of life that it's kind of developing, and that's fine too. So it's kind of serving sort of dual functions, just existing as sort of as a forum for me to sort of talk about machine learning concepts at a more introductory level, while simultaneously identifying people with more advanced backgrounds for.
Yeah, I mean, I don't know if your interests lie in this realm, but like, I feel like there's a ton of people you could interview. Like if you wanted to turn it into like a show where you did interviews sometimes, like it would be super interesting to hear interviews with people. I mean, I like the format of your show a lot.
Yeah.
But I really like listening to just people talk to each other. And I think there's some degree of that's like a universal thing that people like in podcasts, is like people talking to each other because they like the feeling of like being in a social setting when they're listening to a podcast sometimes. But I don't know if that's at all
No, I think that would be at some point in the future. I think that would be a dimension to the podcast that I would like to add to the podcast. At this point, for the next couple of years, I have a bunch of things to say, and I probably would keep having stuff to say, but I think that I eventually would introduce sort of an interview dimension to the podcast at some point. But I'm not at this point. I don't have any plans to do that, and I know that. So I try to I've been sort of I've experimented with different ways of doing the podcast. And
the best trick is to bring on guests and then ask them leading questions. So you you shape what they say, and it sounds like objective truth. That's what I always do. It makes me more convincing.
Yeah,
that's half joking.
Yeah.
So to begin to close off, there's something you discussed in one of your very early episodes. You said the mystery. There's a mystery underlying artificial intelligence and biological intelligence. How do artificial intelligence and biological intelligence differ?
Ooh, how do artificial intelligence and biological intelligence differ?
Do they? Do we know conclusively that they do differ?
Yes, they do differ. I was trying to wrap my mind around that question. Yes, I mean they're totally different, and the real question is, or related question, which is sort of like what do we think the goals of artificial intelligence should be, and like, for example, suppose you achieved, quote unquote, would you think that the goal when you're embarking on a project, one thing you want to think about is, well, what are the goals of the project? What are we trying to do? So if you have a software project, well, what are the software requirements for this project? So you could sort of play that same kind of game with artificial intelligence. What's the end goal? Suppose that we had limitless time and limitless technology and all sorts of resources. What would we declare as a victory? When some people might say, well, if the artificial intelligence was like a human biological intelligence, that would be a victory. Well, other people might say, well, if the artificial intelligence had features that were characteristic of human intelligence, but it was still what we would call intelligent in some sense, then that would be fine too. If you had if we met an alien intelligence, or for example, dolphins or dogs, people might say, well, dolphins and dogs are intelligent in some sense, or an alien was intelligent in some sense, but they're not human intelligent, so they're not really truly intelligent. I think that I think my idea of intelligence is I have my own personal definition of intelligence. I define intelligence to be the ability of a organism or non-organism to be the ability of an entity to be successful within its particular ecological niche. So that's my personal definition of intelligence. And some entities have broader ecological niches than others. So you can have a smart pencil sharpener and you plug it into the wall and it can sharpen all sorts of pencils. But if you put the pencil sharpener on the seat of your car and say, drive this car to the grocery store and buy me some milk, it's probably not going to do that for you. So its ecological niche is when I'm plugged in and you stick a pencil into me, then I'll sharpen the pencil really successfully, but I'm not going to be able to drive the car to the store and buy some milk for you and bring it home. Okay, so humans have a very broad ecological niche, and dogs probably have a narrower ecological niche. We have lots of intelligent machines in the real world, which intelligent, and as I said, I think in my podcast in the 60s, we had 1965, late 60s, we had Samuels, who had a championship checker playing program, which used a combination of both artificial intelligence and machine learning algorithms to learn from experience, and it was able to beat very, very competent human checker players. And the 60s, I tell you that I don't know if anybody is listening knows the status of computers in the 60s, but they didn't have laptops then. The computer technology wasn't very advanced, but this is a very advanced technology. It's a combination of artificial intelligence search techniques with machine learning techniques. When computers had just barely been invented, being able to learn from experience and beat human level checker playing, human checker players who were experts in checkers, and people had said, well, that's not real artificial intelligence. Real artificial intelligence is if you could get a computer program to play chess. Well, that was a lot harder. That took another 30 years or something. But then when people did that, they said, well, no, that's not real artificial intelligence. You have to build a computer that would play Go. And so each time we build something which is sort of artificially intelligent with respect to a particular ecological niche, the mystery kind of goes away. I think the same thing sort of holds with human intelligence. As we learn more about the biology and we learn more about how human intelligence actually works, some of the mystery will go away from that, and the parts of human intelligence that we understand really well, we'll say, well, that's just the amygdala interacting with the frontal cortex in this particular way. When
I had Stephen Wolfram on the show recently, he said, I might be misquoting him, but I'm pretty sure what he said was he came to the conclusion that knowledge and computation are essentially the same thing, which, in one light is kind of maybe puts humanity in a less prestigious light, but in another angle, it's great because we can compute. I mean, the whatever prestigious stuff humans have, we can do with computation.
I think that I think I would agree with that. I think of knowledge more as I think if you take the view of knowledge as more of sort of active knowledge structures, then I think that one could make a relationship between computation and knowledge. But the sort of concept of computation and knowledge probably needs to be carefully defined.
Right. Great. Well, it's been a great conversation, Richard. Thanks for coming out to Software Engineering Daily. I hope to have you back on in the future. This was a really, really fascinating show. So thanks.
Sure, it was my pleasure. Thank you so much for inviting me
Absolutely.
to participate in your podcast.